Welcome back to this last part of this week's lectures. In this concluding sessions, we're going to look at a couple of uh, ancillary topics which are also equally important. So we spoke at length about ETL, right? Extraction, transformation, loading. And in that context, we spoke also about different patterns. In which case, what is ELT then, right? What does this terminology mean? Excuse me. To understand this, we need to understand how did ETL evolve over a period of time. So, if you remember this diagram that I drew in the first slide, E is really the extraction. The ETL tool or software controls the extraction, but there is a very strong dependency on the source, the OLTP system for that extraction. The transformations themselves happen in that as the data flows through the ETL tool, which is typically operating on a machine or a cluster of machines. Then the load happens to the OLAP system, like a warehouse or a data lake or a Hadoop or whatever. And when the load happens, it's happening with the protocols, with the specific interfaces those systems actually themselves support. So the dependencies on the source and the destination are quite strong, right? ETL evolved as a centralized mechanism, like we saw in the first lecture in this week, or rather the first video of this lecture, that the centralized mechanism became easy for people to control. What ended up happening though over a period of time was, if you really looked at the computational horsepower, the resources available, right, and the speed at which you could execute a job, a data processing job especially, and if you plotted the relative sizes of the software and the clusters and the access to resources, the OLAP system is actually much bigger compared to the OLTP system, compared even to the ETL software system. So in fact, in reality, the ETL software system is very likely to be the weakest link. So if you're going to extract data from a source database, then you don't have much control on how big that source database is, right? Because it's usually the prerogative of the source, which is the business team which is controlling that source. The transformation tool is usually going to be your weakest link. And so the data pipes through that transformation tool and eventually goes into your OLAP system. And the OLAP system is this big system which has so much resources, so much computational horsepower, that's actually getting underutilized, right, for the purposes of data loading, data transformations. So the only thing that you're doing with the OLAP layer is load. Now, this by itself is actually not a problem. This becomes a challenge, or this becomes the disparity becomes stark the moment you look at big data. So the volume of data that comes out of this OLTP system is huge, is massive. The velocity with which that extraction happens is also going to be very large. So if this teeny weeny measly ETL software running on this single machine or a small cluster is having to do that volume of processing at that speed only to populate an OLAP system that's much bigger, that has much more computational resources at its disposal, it's a mismatch. That mismatch can very quickly place this ETL software in the firing line and make it a bottleneck. The moment that it becomes a bottleneck, it becomes expensive to scale, it becomes expensive to deal with things, and you no longer have access to the data in as quick a manner as possible in the OLAP for various downstream purposes from the OLAP. So that's why this architectural pattern became a challenge in the world of big data, in the world of not just Hadoop, but even some of the large-scale data warehouses as well. So then came the realization that you cannot get away from the extraction from the source system, right? That's where the data belongs, right? We can't really do anything about it. You have to load the data into the OLAP, because that's when everything else becomes possible within the OLAP, including business analysis. So the only thing really you can play with is the T, right? Where does the T happen? And that's where actually the ETL software running separately on the machine becomes the bottleneck, like we spoke about. So what, therefore, became the approach was to push the transformation into the OLAP as opposed to doing it outside in line as the data is moving through. So in this kind of a architectural setup, then the core prerequisite in order for you to do well at the scale of big data is to have a data pipeline which allows you to not only do extractions fast but also do loads fast, and that's it, right? You don't need to worry about transformations, at least for now. And obviously you need a good network to connect these two machines together, etc. But that's the infrastructure side. But at least if you can get the data fast into the OLAP system, then I can worry about doing transformations within the OLAP system, leveraging all the compute horsepower I have available, and control for the speed it takes, the time it takes, and the SLAs that I want to promise. That's what ELT stands for. It's the same extraction, load, and transform, but instead of doing transformations before loading, I'm doing transformations after loading inside the OLAP system, leveraging its compute. Now the question becomes, what is the ETL software doing now? Right? It's now catering to an ELT pattern, and in catering to the ELT pattern, it actually does not really do any data processing by itself. It's actually doing control more than data processing, right? It's controlling the extraction, controlling the loading, controlling the transformations. Then, is it really adding value? Some technologists argue not really. You don't need an ETL tool in the classical sense anymore in this ELT pattern. Because control can be exercised through other mechanisms, like for instance a scheduler, and we'll talk about that in the next slide. Some others argue that the centralization of governance, the centralization of the standardization patterns, of the patterns that we saw in the previous slides, there is still merit in doing all of that from a single ETL tool as opposed to reinventing the wheel. The question then becomes, why can't we standardize and centralize within the OLAP? Because the OLAP is anyway a centralized layer for analytics. If this is a centralized layer, why do we need a separate tool sitting outside that's trying to standardize on transformations? So the transformations themselves are happening within OLAP. So then the entire movement towards creating data catalogs within the OLAP, creating data management within the OLAP, all of that became a popular set of technologies. And today, if you see, most cloud vendors of OLAP options, like for instance the data lake or data compute using NoSQL, ETL jobs within the cloud, all of them have a notion of data catalog. All of them have a notion of metadata management. All of them have a notion of standardizing on patterns which are typically encountered, like duplicate checks and stuff like that. Why? Because the OLAP layer itself becomes the ideally well-suited layer from a perspective of big data to standardize on transformations and to also have the execution of transformations happen within. So the control itself is shifted to the OLAP. So much so that it's now the cloud vendors who are giving OLAP options who go into the source system and do the extractions. You don't need a separate tool anymore, right? So for instance, in Amazon, there are mechanisms. I forget what the name is right now, but I think it's the database service or some such thing. I forget the DMS. Yes. DMS is the name of the tool in Amazon. So DMS is very good at, for instance, extraction from a source database. So you don't need a separate control layer. You just use DMS. It goes inside OLTP, does the extract, does the load as well, and then you follow it up with a bunch of transformations expressed using like Spark on Glue or Spark on EMR, Elastic MapReduce. So that's an example. Okay, so what are the biggest advantages for why ELT makes sense as opposed to ETL? Obviously, performance, right? You now have access to much bigger compute, so transformations can go as fast as you want. And if it's not going faster, just get better compute, better OLAP. At least you have a better chance of meeting your SLAs in this architecture as opposed to an ETL architecture. The second biggest advantage is that you now have access to the raw data as soon as it's available from the source. And that is actually very useful for certain kinds of use cases like data science, or even, for instance, for real-time recommendations, real-time machine learning, real-time scoring. So, okay, let's contrast this with ETL. In ETL, before the load happens, transformations happen. Transformations take their own sweet time. That happen within the transformation machine, the ETL machine. So by the time you get access to the data, at least the amount of time that's required for transformations to have done would have elapsed. Whereas in this ELT approach, as soon as the extract is done, the load is done. Right? Obviously, the time it takes to load is of course there, but the time for transformations is not factored in. So you have access to the raw data pretty much immediately as soon as the source makes it available, and you can choose to do things with it. Right? You can choose to do a lot of very interesting patterns of processing. So one such pattern of processing is something called as the Lambda architecture. What does a Lambda architecture do? It says that as soon as this data is available to me, I'm going to kick off a real-time pipeline which computes things in real time and it gets me answers in real time. While the classic ELT approach, the classic transformations, they take their own sweet time. They take 30 minutes, 1 hour, 4 hours, 8 hours, whatever it is. And they compute an answer at the end of the day, which integrates all of the data, which does all the good stuff that you would expect from a single version of the truth, and gets you the final answer. What's the difference between the two pipelines? The real-time pipeline, the top half of the Lambda architecture, has executed really fast as soon as the data is available and given you an answer in a jiffy. Is that the final answer? No. But is that an answer that's usable? Yes, for certain kinds of use cases. Like for instance, let's say the business wants to know what is my business today as of the latest timestamp, and I might be interested in this because I've done a special Diwali sale. So I want to know, what's the latest business as of, let's say, 12 p.m., 12:05 p.m., 12:10 p.m., etc., as the day progresses, because I want to dynamically adjust new offers, make new discounts available, etc. To do that, real time is of essence. I can't wait for end of day to actually get an answer. So in the Lambda architecture, the load happens fast, right, into the OLAP system. It could be a message queue, for instance, right? It could be a S3 bucket, doesn't matter. I immediately get the answer out through real time. And separately, the accurate answer, which is business certified, which is finance consistent, all of the good stuff, happens as a separate process. So when the separate process executes, the batch process executes, it's populating the same functional view, right, at the end of the day, which the business sees, but then business is explicitly told that some things are real time and therefore they need to expect a little less consistency. And some things are batch and the batch ones will be more consistent. So this entire architecture becomes feasible because of ELT. Right? So that's something to keep in mind. So very interesting benefit of being able to access the raw data as soon as it's available. The third interesting benefit is that if you scale the OLAP platform, automatically transformations also scale and vice versa, which means the control of how much data changes, right, in terms of volume, velocity, and how do you react to it. It's actually a lot more under your control because it's just one system to worry about. In the ETL systems, in the ETL architecture, the ETL tool has its own machine. You have to worry about that. That's controlled by somebody else. The OLAP system is controlled by somebody else. You have to worry about both these sets of resources, and you have to worry about the bottlenecks that the ETL tool creates. Here, it's just one system. Obviously, the one system has multiple computes associated with it, and some of the computes scale linearly, some of them scale decoupled manner. So you have to worry about that, obviously, but then at least it's just one system to worry about. That's the third advantage. Alright, so what you'll see in the real world is ELT. Right? Very rarely ETL gets used nowadays, especially in big data. We hinted about scheduler earlier. So the fact that control is with the ETL tool, which dictates what needs to happen when and how, etc. And that centralization of control is actually a good thing because you get to have governance, you get to have, various good properties associated with the data processing. So let's take a look at what those are. So in the world of big data, in the world of ELT, the scheduler plays the controlling role. And the scheduler is actually a very important piece of software. What does it do? It figures out which tasks can be run in parallel and which tasks can be run in should be run in sequence obeying dependencies. It handles failures automatically, whichever it can. Like obviously, it can't handle functional failures. It can't handle failures at the semantic layer or data type mismatches or things like that. But it can handle failures of machines failing, tasks failing. So you can program it to say, let me rerun the job, as an example. It also provides the state of operations visibility to any consumer. The consumer could be a business, could be some other data pipeline that's waiting for this particular job to finish, right? And that's a very crucial role, because go back to cloud native principles, right? Observability. How does observability come about? It's because you provide full knowledge about what's actually happening for anybody to consume. And when you do that, obviously this means machines have to consume, not just humans. When you do that, then automation, which kicks in from another machine, knows what to do, right? When a particular operation is done or not done or failed or not failed, and then kicks off appropriately. So a scheduler does these three things as like the key responsibilities. So if you take a look at how does it figure out what task to run in parallel, it comes down to configurations. It comes down to how you specify to the scheduler what the ETL jobs or ELT jobs should do. And therefore, it also maps out its own dependencies, which data set needs to be ready for me to do my next thing, which data set, which source system needs to be ready, which destination system needs to be ready, all of those good things. It also is time bound, right? For instance, you can say, I need these things to happen, rather I need these tasks to start exactly at a particular time, like that ETL job for the revenue per business day, right? It ran at 8 a.m. every day. So that's a scheduling task, obviously, but then that can't run without the previous day's jobs data being available. So you can make both of those as constraints in the scheduler. So the schedule that the scheduler uses is typically as per business time, because ultimately what's getting populated is a target table in the integrated layer. The scheduler runs themselves, though, are on operational time. So if you go back to the ETL example, ETL ran at December 2, 8 a.m. for the business revenue to be computed per business day. So that's operational time. But the schedule was actually being run for populating December 1's revenue, December 2nd's revenue, December 3rd's revenue, which is actually business time. So the scheduler is one of the few softwares which transcends both these times, right? So again, you'll have to think about what does handling failure mean, right? What does state of operations visibility mean in this context? So the scheduler has to have, there are two salient facets to the scheduler. One is it needs to know when to start. Like we spoke about just now, 8 a.m. start on a particular day, every day is one such time, right? That's an operational time. Or 100% data availability, right? Which means I can start the moment I know all of the data for a particular day is ready with me. The snapshot is ready with me. How do I know that? Maybe the source system is indicating that to me by placing a special record in a special table that I can extract and compare. Or my extraction job that I run finishes successfully and then goes back and checks and finds there's nothing more. Right? So that's 100% data available. So I can trigger the job that needs to run from that point on. Notice that if I do that, it's trigger based, it's not schedule based. Right? So it's on time based rather. It's based on availability. So it's trigger based. Or it could be a both. It could be a combination of both, right? So I run a particular time, but I don't start the execution without knowing that 100% of the data is available. So the scheduler is also responsible for denoting closure of a business day snapshot. You could embed this logic in the ETL, right, or in the ELT, but that's not recommended. Ideally, you would just put as part of your scheduler that one of the last sequence of activities that closes a particular business day, a special kind of a state change or a special logging message or whatever it is, which denotes the closure of a business day. Like could be a control table as an example, right, where you just go and enter there saying December 1 is done. So then the business team that comes and takes a look at it says, yeah, December 1 is done, so I can start using that data for analytics. So the scheduler is a very, very important piece of software. So what are the types of scheduler that you'll see commonly in the world of big data? The older examples were all based on Hadoop's ecosystem. So we spoke a bit about Uzi as being one such example in week 4's lecture. The more common example, though, that you'll see quite frequently is this tool from Airbnb, which is called as Airflow. Airflow is actually very, very popular. Airflow constructs tasks in DAGs, directed acyclic graphs. Like you might remember that term from the previous lecture on Spark. So again, the notion of a DAG is very useful to think about which tasks can be run in parallel, which tasks need to be run in sequence, where the dependencies have to be obeyed. Airflow is very good at cron style scheduling, obviously, which is run a particular job at a particular time every day, every week, or whatever, right? But then it's also very good at trigger based. So you could say trigger the job as soon as the data is available. Data is available is indicated by the presence of a folder, the presence of a file, presence of a marker, whatever it is. Airflow is also very good at stitching together dependency views across Airflow DAGs. So you could run one Airflow DAG for one ELT. You could run another Airflow DAG for another ELT, which picks it up from here. And you could get a centralized view of all of these DAGs, so that you know exactly like what is actually causing the problem, what is dependent, and which job has not failed, therefore which job has not succeeded. Those kinds of things. And one of the best things about Airflow compared to, let's say, Uzi or anything else, is that it segregates this notion of time in a way that's a lot more cleaner for you to understand. Operational time separately from business time. You still have to model business time though, right? Because that's very specific to the business. But the operational time, the concept of operational time becomes something that you can easily deal with from a UI and get to understand which operational runs have actually done successfully. So data ops becomes a little easier. All right, so that's the discussion on scheduler. So in practice, to sum it all up, you will have in your practical big data project, very likely an Airflow job, or in the world of cloud, there are cloud equivalents for Airflow also, right? So you might use one of them, like in AWS it's called as step functions. In Microsoft, I think it's called as Azure Badge. I'm sure Google has its own equivalent. So yeah, so you could have those kinds of schedulers there, those kinds of dependency trackings there. So in practice, you'll have one scheduler instance. You'll have an ELT, which is usually expressed in the form of Spark, by Spark, as an example. All the metadata, reference data, all of that is getting managed in the data catalog. And then you'd have your patterns coded up in Spark, and the control table stored up in some kind of a simple database like Postgres or MySQL. So that becomes your entire data processing stack, in effect. All right, so I'll close this week's lecture with a brief discussion on a couple of advanced topics. These are advanced because discussing them at length is outside the scope of this course. There are a lot of nuances to this, and it's best that you read up on some common popular literature that actually discusses this, if you're interested to dig into the details, right? So for instance, Spark does it very well. So if you look up Spark's documentation, they discuss these two topics at great length. So let's discuss the first topic, right? Late arriving data. So what does late mean? Late is from a perspective of operational time. And late also pertains to the event time. So event time not matching with operational time. That's exactly what this definition of late is. Let's take an example. I have data that corresponds to yesterday's payments. I've consolidated all of that. Today morning, 8 o'clock, this December 2nd, 8 o'clock, I run my ELT to get me the revenue for yesterday. At 9 a.m., I've gotten a file which has December 1's data. So what does December 1's data mean? It means that the payment time has entries which correspond to December 1's timestamps. But operationally, I've got the data only at 9 a.m. How do I deal with that? So this could happen this could happen in reality for various reasons, right? One, the source system that's publishing it potentially missed out on this particular file and it figured it out later and sent it out, or it failed while it was transferring all the files. And the ELT job thought that the data was 100% available and complete, and so it started to run. Or worse, it just ran on a schedule without checking for data availability of 100%. The third scenario that's possible is the data was not reconciled yet by the source system. So remember, we spoke about source systems having different versions. So maybe this data is actually from an older software, and that older software did not finish its execution. So it got delayed, and then finally it sent it out much later. So there could be many scenarios. So in which case, how do you deal with it, right? So the December 2nd, 8 a.m. job that you ran, let's say it ran for 30 minutes, it computed the value for revenue for December 1. The answer that it computed was obviously wrong. You would know that only later, but when it finished execution, it computed a value, and as far as you know, that value is right. So you go ahead and publish that. But when the 9 a.m. file comes in, corresponding to December 1's data, you have to go back and recompute the ETL. So because the data is now fully complete, hopefully, right, there's no more later arriving data beyond that. So then what you do is you run the same data again, right? You run the same ELT again. If you run the same ELT again, you refresh the business value, which is good, which can happen. And that's one way to deal with it, right? Business has to be informed that, like, look, even though the value is available from 8:30, there is a chance that it can be updated again or refreshed again based on later arriving data. And if business is cool with it, that's fantastic, right? So you move ahead. But this makes the crucial assumption that if I simply rerun that ELT, I'll get the most recent values. That might or might not be true in all cases. It depends on the business logic. So the case of calculating revenue for a day is actually something that's called as associative, as a computational model. So it's associative and commutative because it's just a simple sum, right? You're just summing up the payment amount column. So you're summing up for 80% of the data, 20% of the data comes at 9 a.m. So you take the sum of 80%, you include the sum of this 20%, and you get the final sum. Nothing else changes. That's great. But sometimes you might not be able to do it because you refer to the previous day's business value and you compute something else here. And so when you rerun the ELT job, you cannot just take from what you left off with and then carry on. So the example here is balance. So let's say you're not computing sum of revenue, you're not computing revenue for a day. Instead, let's assume you're computing the cash balance available with you. So the cash balance is a running total, right? It was last updated for November 30th. December 1st is what you're doing at 8 a.m. in the morning. The cash balance gets computed. And then now you have the 9 a.m. data coming in. The 9 a.m. data will allow you to take the cash balance of the partially computed 8 a.m. jobs values and then add the 9 a.m. jobs values, and then you get the final answer. But that may not be the right way to go about it because the way you order the data might be different, right? The later arriving data could be interleaved with other genuine data that you've already computed. So the right way to go about it is to go back to November 30th's cash balance and redo the entire job of December 1 with the 9 a.m. data also included, right? So that's one way to deal with it. There are many, many different ways to deal with it based on what later arriving really means. So the operational time associated with it is something that you benchmark and then, watermark rather, and then you use watermarks to figure out when is the next bunch of data that you want to compute. One of the advantages of Spark is that it has this watermarking concept already natively built in for its RDDs, for its data frames rather, and then you can then run continuous jobs. So we spoke about schedulers, we spoke about ELT running at 8 a.m., finishing at 8:30, and then that same ELT will run the next day at 8 a.m., right? So after 8:30, it stopped because it's computed the final values. That's a scheduled job. But in the case of late arriving data, because you never know how late something can arrive, so you have this concept of watermark that Spark actually natively provides support for, and it also has this notion of continuous jobs. So you run this ELT continuously, And the ELT runs only if there is new data. And if the new data comes in, it automatically gets checked against the watermark for yesterday and figures out if it's late arriving or it's genuinely new data for today. And appropriately, that continuous job picks up and runs because it's trigger based and the data is available, so it runs. So it's actually pretty powerful in what it supports as a paradigm. The next topic here is out of order data, and this is a lot more complex to deal with, and it's very, very use case dependent on how you deal with it. But in a sense, if you get data that belongs to different time elements in different order, in random order, your job as a data warehouse creator or an OLAP creator becomes that much more complex. So what is the challenge here? So let's say you're creating, again, business time based snapshots. And if the data starts getting interleaved, right, you suddenly not only get late arriving data for December 1, but you also get late arriving data for November 30th. But you also get December 2nd's data. And it's all jumbled up. Then you have to know how to deal with it. The simplest thing to do is, of course, segregate based on time, go back and run the ELT for each of those dates. November 30th, December 1. And December 2nd is not done yet, so you wait. But the more complicated thing to worry about is, those states that you have to maintain, which depend upon the order. So the cash balance is an example, right? You're not interested in cash balance at the end of the day alone, but you're interested in were there any situations in the middle of the day when you ran out of cash? Because the sequence of payments that were made were not sufficient to the sequence of outflows that you sent out, that you withdrew from the books. You would not know that if you didn't know how to order the data. And if the data was coming out of order, and especially if it's also coming late, then you really, really do not know what was the situation at that particular point in time. So out of order data has its own nuances. Unlike late arriving data, this is a lot more use case specific. Even late arriving is actually use case specific, but here you really need to know if your use case demands that the ordering of the data matters or not. So accordingly, you'll have to deal with it. Thank you. So with this, we've concluded this week's lecture on ETL's patterns, ELT. I hope you take away the message that the patterns are actually broadly standardized, right? There are only like a finite number of things that you do with data typically, as far as data preparation, data transformation goes, to create that integrated view for analytics. Data science is actually typically not even requiring that. In most cases, data science just requires raw data. But as big data engineers, you have to be familiar with these patterns because there's nobody else who's actually going to do this, right? The source does not care. The business does not care. The business just asks the question and expects answers. So then the data engineers are left to actually fend for themselves and solve these problems. I hope you've taken away from this week's lectures, ways in which you have solved the problems as well. Yeah. So thanks. Looking forward to next week.